Yes.
Sorry to bug you already, but
No.
I saw this thing about machine learning, like they had a computer taught the computer how to play Super Mario.
Yeah.
How would you get software to use software like that?
Okay, so it's called reinforcement learning, and believe it or not, we're going to talk about that at the very end of this. But basically, what you do is you give a computer a goal, and like say the goal is to get to the end of Mario, and then you have the computer read in pixels, like just raw pixels, and also the score of a game. Does Mario have a score?
Yeah, it does.
It does? Okay. So you want to maximize that score. So you have the computer read the score and also what's going on in the screen, and the computer does random operations to maximize that score, right? And then as it trains over and over and over again, it finds out what actions it needs to do, and it learns from those actions in order to maximize the score. So yeah, we'll do a good long talk about that. I think I'm going to talk about like half hour on that because it's like really one of the most exciting parts of machine learning right now. Are we at 1:15?
Yeah.
Okay. All right. So
Sorry, what are we what?
at 1:15 o'clock.
Oh, okay, yeah, I guess so.
Okay. All right. Well, you guys, welcome to Machine Learning 101. I'm really excited that you guys are here. We're going to be covering machine learning and artificial intelligence. Sir, what's your name?
Philip.
Philip and
Lynn.
Philip, Lynn, and
Will,
Philip, Lynn, and Will. Okay. Welcome to the class. I know these two guys. These guys are veterans. Oh yes, Mike and Jonathan. Okay. A little bit about me. I am a software developer. I specialize in machine learning and artificial intelligence. You can find me at tylerseward@gmail.com. All right, so here's what we're going to talk about. We're going to talk about what machine learning really is because there's a lot of news going around, a lot of people speculating, a lot of people who have no idea what artificial intelligence is talking about it. So we're going to go over what it really is. Also the how. This part is not very fun, but it's really, really important. And I was so sad to learn that this is like the most important part of machine learning is the data preparation. So data is your only friend and your worst enemy, numerical and categorical data, just a whole bunch about data. Part 2, training a model, which is how you get the model to learn. Then we talk about some algorithms, and then here's the fun part, deep neural networks. Okay, that's like the cool part. Everybody's heard of like deep learning, right? No? Oh, okay, that's just me then. All right, so it's like a buzzword in the tech industry. They'll say, oh, it's deep cars, deep toasters, deep this, deep that, and it's just using neural networks. All right, so the what. First, we're going to go over what machine learning and artificial intelligence are. This is not how AI actually works, but I thought it was really funny because I saw it from a conference. And this is what people sometimes think AI does. You put in data, AI does something, and then output is magic. All right, so definitions. Artificial intelligence is getting a computer to do something that normally requires human intelligence. For instance, driving your car is something that up until recently required human intelligence. Now we have self-driving cars. So getting a computer to do what a human normally does, self-driving cars, is artificial intelligence. Machine learning is a specific type of artificial intelligence where instead of telling a computer, turn left, turn right, go straight, we give a computer a huge amount of data and we ask the computer to learn on its own. Like instead of, let's say you have an intelligent child in a class, you can either teach him grammar rules, writing out each word on the board, or you can give him a really big book, like some kind of novel, and he can just sort of learn from that. So machine learning is giving a computer data so that it can learn on its own. And of course, you set the parameters for how it's going to learn and what it's going to learn from that data set. Okay, now we're going to talk about a couple of really important types of machine learning. Okay, classification is very simple. It's dividing things into groups. Like you get your groceries home and you have apples and you have tomatoes and you have broccoli. So you say, okay, apples, that belongs to fruit, broccoli belongs to vegetables, and tomatoes belongs to, I'm not sure. I think some people say it's fruit, some people say it's a vegetable. So you figure out which category you want to put it in. So that's what classification is. Okay, so we're going to go over a really simple example of what classification is. So you have three animals over here, a cat, a snake, and a person. The cat has 4 legs, a snake has 0 legs, and a person has 2 legs, right? These are typical lengths for those animals. There's a cat, it's 2 feet long, snake is 4 feet long, and a person is me, I'm 6 feet long. So we've got that little graph, and then if you've taken high school algebra, you know how to put things on a graph. You got the snake here, it has 0 legs, C number of legs, and then we go up and it's 4 feet long. So the snake is a dot at the intersection of 0 feet and 4 feet, or 0 legs and 4 feet long. Same for the human, 2 legs, 6 feet, and then a cat, 4 legs and 2 feet. So we've just classified some animals. So this is how you would train an artificial intelligence. You would train using a data set and kind of like a graph like this. Okay, so what you want to do once you've trained a model is perform what's called inference. You want to compare it to new things. This is how you do object detection. So we have this new animal right here. It has to be either a snake, a human, or a cat. And we have a new animal right there. Any guesses as to what animal this blue one is?
Cat.
Yes, very good. It's a cat because...
Did you call it pinprick?
What?
What term did you use to describe?
Inference?
Imprint, okay.
Inference.
Inference.
Yes,
Okay.
it's like you infer something.
I get that.
Because you have a lawnmower, I can infer that you mow a lawn and that you are a homeowner. All right. So yeah, we put it on there. Cat. It's just a shorter cat because it's 3 feet. Okay, or a longer cat. Okay, so image recognition is really cool. It's what they use for facial detection, which is a little bit creepy, but they use it for a lot of other cool stuff. There was one guy who, he was tired of his cat coming into his house carrying a mouse in its mouth, carrying dead rodents. So what he did is he set up a camera and he took thousands of photos and he made it so that the cat door would only unlock if his cat did not have a mouse in its mouth. I've done this with like a laser turret that follows my cat around. It can detect where my cat is and it'll chase him with a little laser. Yeah, object detection is super important and very useful. It's how Teslas can do self-driving. They just have cameras around them that can detect what's on the road and stop signs and speed limit signs as well. All right. This is a picture of a cat. We're going to use him for an example. So if you look at a picture like this, pictures are made up of pixels. They're made up of tiny little dots like these. And each dot is a different color, right? These dots are black, these dots are white, these dots are light brown. So for every pixel, it has a value that is 3 numbers. It's how much red is there in this pixel, how much green in the pixel, and how much blue in the pixel, right? So every single one of these has a different value. The black ones are probably 0, 0, 0 because they've got no colors, whereas the lighter ones are, higher numbers of red, green, and blue. So these numbers for the pixel can just be represented by the computer as just a string of 3 numbers, right? So those easily go into a computer, but we're not just doing it for one pixel, we're doing it for every pixel in that photo of a cat, and there can be millions of pixels. So we put all of those pixels into the computer, we turn the image into just a bunch of numbers, and we tell the computer, this is a cat. This collection of numbers is a cat. And so if we do that with a lot of images, like thousands of images, the computer starts to pick up patterns in the numbers. And the next time it sees a picture of a cat, it can say, okay, well actually this picture has similar number patterns to the one that I just saw. So I think that this is a cat. And then it'll draw a box around it and it'll give you a percentage, like I'm 98% sure that this is a cat. So also you can do this on the Raspberry Pi. Like we were working on setting that up. That's the demo that we were trying to do the other day. All right, so, yes?
So how does it compare the numbers? Does it look at them side by side somehow, or does it go through them and tally every time they're slightly different, or what kind of...
That's a really good
When
question.
you get a number at the end that tells you how similar they are?
Okay, it's a complicated answer for that. It uses deep learning. So you have, on this side, you have 10,000 images of a cat, right? And on this side, you just have the label cat, just the word cat. And so in between, you have a deep learning network. A deep learning network is something that makes its own equation. It's kind of like a...
It's like a filter kind of, isn't it? Where
Yeah.
the data's coming in and it won't ring like the cat button unless it has enough positive data to make it sort of hit that.
After it's trained, yes. But before then, remember we said it's a smart child, right? AI is like a smart child. So you give the smart child some data, and the child is going to discover a pattern in that data. It's going to make an equation in its head. It's going to say, okay, this certain collection of numbers, it could be whiskers or like fur or a cute little face, equals cat. So it's got all these photos, and it builds its own equation to take those numbers from the photos and turn it into the label cat.
Okay.
So we'll talk about how that network works later on.
Yeah, sorry to jump ahead like that.
No. So you're doing fine. Any questions you guys have, ask me. I mean, the worst I can do is say, hey, we're going to cover that later on. So, all right. Yes.
Before we get too involved, is machine learning and artificial intelligence interchangeable terms?
Nowadays, yes. Machine learning is a particular type of artificial intelligence. They say that if you're doing a PowerPoint, you call it artificial intelligence, and if you are talking to developers, you call it machine learning. So it's
Or technical
yeah,
definition?
machine learning is artificial intelligence. Artificial intelligence doesn't necessarily have to be machine learning. Artificial intelligence is a big umbrella, and machine learning is just one of the spokes.
It's mind-boggling the amount of computing power that must be necessary to take all these individual pixels from all these thousands of pictures and come up with cat.
It's pretty nuts, but I mean, hardware is being designed specifically for these types of programs. Like the computers that you have right now just have a CPU, and they would take forever to train a program like with the cat, like we just saw. It would take days, weeks, maybe even months. GPUs, or graphics processing units, are they're common in video games, or common in use for video games and like gaming consoles, and they just so happen to be amazing for artificial intelligence because they can handle many transactions at once. There's a new kind of processor coming out called a TPU. It's about 4 times as fast as a GPU, and a GPU is about 60 times as fast as a regular computer. So the hardware is catching up with the software. But you're right, it is pretty intensive.
If you're working in machine learning and you want to get a grant from the US NIH or NSF, call it artificial intelligence. Artificial intelligence in the title.
That's another interesting thing. Good point, Mike. There are tons of grants out there. Like I've been contacted by people who want me to apply for grants for artificial intelligence from the government. The government wants to invest money in artificial intelligence. So I don't really have any ideas right now that I want to pursue using government funding, but if I do, I will talk to them. All right, so how many of you recognize this person? No, very good. Okay, how many of you recognize this person? Perfect. You guys are very honest. I've had people lie to me and say that they do recognize these people. Neither of these people have ever existed. I would like you to go in your browsers right now to thispersondoesnotexist.com. Both of these images were created by artificial intelligence. Neither one of these people have ever existed. What they did is they fed 50,000 images of people into a neural network, and then they said, hey, create an image of a face for us. And these are what came out. Everybody have one of the images?
How many do they have? I don't want to look at this one anymore.
No, every time you recycle the website, it creates a new one just for you.
Looks like my boss.
It looks like your boss? Maybe you should send it to him.
I don't like him.
Okay. You don't want to give him any presents. So one interesting thing is a way to tell that these are fake. If you look at the teeth, they're just a little bit off from center. The ears are usually weird. And also, yeah. Well, no, I'm looking at your teeth. They're a lot better than hers. I mean, look at that. Her nose and her teeth are going in different directions. Another interesting thing is the background. There's nothing identifiable in it. Like if you look at this from far away, you think, oh, you know, that's leaves. But if you look at it closer, there's nothing that you can identify as a real object. Okay, so we looked at thispersondoesnotexist.com. So that is classification and image recognition and object detection. Okay, so prediction. When people talk about AI can predict the stock market, AI can predict the future, predictive artificial intelligence, this is what they're talking about. And it's actually pretty similar to, you know, in high school where you just made a graph, you know. So we're going to talk about that. Okay, another easy example. I have 3 friends. One is named Bob. He's a very short guy, a wee little man. He's 4 feet tall and he weighs 100 pounds. I have a friend named Mindy. She's about 5 feet and she weighs 150 pounds. And I have another friend named Jack who's about my height and he weighs 200 pounds. These are my friends, right? And I know how much they weigh because, you know, we're on a friendly basis. And I decided to, they don't know about this, but I decided to graph them on a chart. We got Bob here, 4 feet tall, 100 pounds. Mindy, 5 feet tall, 150. Jack, 6 feet tall, right? So I met a new person named Mo. Mo is really tall. Mo is 7 feet tall. And I want to know how much he weighs, but he's big and he's scary, so I don't really want to ask him. So I use my graph and I say, okay, given that these people are this height and they're this weight, I want to guess how much does Mo weigh and see if I'm accurate. So I draw a line, right? And then I take the intersection of 7 feet on that line, and that's where Mo is. So I guess that Mo is around 250 pounds, right? So that's a pretty fair guess. And then okay, so whether that's correct or not, that is what my guess is for Mo. And this is how we use regression. This is how AI can supposedly predict the future by analyzing past trends and where they're going. All right, so now here's a question for you guys. What if we add another dimension? What if we add his age? Like right here, we have height by weight. That's only 2 dimensions, right? It's really easy to plot on a graph. But what if we add age? That's a 3rd dimension. You're going to have to plot a graph like this. It's going to have to be a 3D graph. But what if it's 4 dimensions? I can't really think in 4 dimensions. I can't draw a graph in 4 dimensions. What if it's 7 dimensions? I've seen tables that are 40 million columns long, 40 million dimensions. eBay uses those. So how can you possibly wrap your head around this? What you do is you use machine learning, because humans can only think in 3 dimensions, or you know, however many, and we can only draw graphs in 2, but a machine can think in all of these dimensions at once. It can draw a graph of all of these things, and it can find patterns. Like for instance, we might not have known that there is a pattern between a person's address and their height relative to their weight. And we wouldn't be able to figure that out unless we used a machine to figure it out for us. Or maybe a correlation between their height and the number of pets they have. All right, so data preparation. This is probably the hardest and most important part of machine learning. I told you guys I was really sad. When I was first learning about artificial intelligence, I thought it was like, oh, it's magical, robots and stuff like that. And then unfortunately, somebody told me that 80% of your time will be spent preparing your data to make sure it's good, and 80% of machine learning is preparing your data, and it almost doesn't even matter what machine learning method you use as long as your data is good. So, all right, so yeah, data preparation is even more important than algorithm selection. Well-prepared data gives you great performance on the model, even on simple machine learning models. So like when we were talking about Mo, when we say performance, what we're saying is how well does that line predict Mo's height, right? If it's terrible at predicting Mo's height, then it's bad performance and we had bad data going into it. All right, so yeah, and even just like good data equals good performance, bad data, data that hasn't been properly prepared will give you bad performance. Okay, so let's take a look at this. Can you guys spot any errors in this data?
Question mark.
Bob's age.
Question mark is very good. You said Bob's age, perfect, very good. Yes, this number is out of range. Nobody's 132, and there's a question mark right there. Perfect. Anything else?
I doubt Bob's only 4 feet tall.
Well, okay, let's pretend he is. Let's pretend that's correct and he actually is. So,
Mouse.
well, I did that to be funny. So that one is accurate. And are there any other errors that you guys see in here?
Blank spot.
Yep, blank spots, perfect. Perfect. Blank spots will throw things off. Okay, so yeah, we talked about that. You guys did very good. So there are two different types of data in this table. There is numerical data and categorical data. Numerical data is on a sliding scale. You know, it could be from 0 to a billion, could be 5 to 10. It's numbers, but it's also on a sliding scale. And you could be in between numbers, you could be one up, you could be one down. It's like age is a numerical variable. Categorical is something that you use to divide things into categories. So it can have multiple different entries in it. So for instance, let's see, Bob is a meat eater. So if we had more meat eaters on this chart, we could divide them into the category meat eaters. Same for Mindy, her diet consists mostly of donuts. So if we had more donut eaters, we could divide them all into the category of people who eat donuts. So is that clear? Numerical versus categorical? Okay, perfect. All right, so for this particular experiment, it is highly unlikely that address is going to play a valuable role. Because if we're talking about, height versus weight, address, even though I said, it might be before, it's probably not going to matter in terms of what your weight is versus your height. So we can just delete it because it's not that important and it's got blank spaces in it. So you can just delete an entire column or an entire row if it's not very important and there are blank spaces in it. Okay, also you guys noticed the error, very good. He's probably 32. I mean, if you have an error, you can just guess it, or again, you can delete the row if you've got enough data. All right. And also, pescatarian and fish, it's the same thing, right? People who are pescatarian, they eat fish. So you could probably combine these two categories because they're the same thing. Combining categories is totally okay as long as they're similar enough. All right, so when you combine a category, you put a dash in between them, right? So if we wanted to combine all three of these, we would do meat dash pescatarian dash fish for all these. It's okay to combine categories if you want to, if you need it. All right. Okay, let me see.
What if you added a column for number of children, but they all had 2 kids?
Ooh, that's a good question. You would not use that column, likely, because, as I said, it's about creating an equation. Your input data to your output data, right? And if it's all the same, then it doesn't matter in the equation. Yes?
What if you have a huge amount of data and no one's going to go through it and find all the question marks and blank spots?
Well, you will often be working with a huge amount of data. And you'll have to go through and find all the question marks and blank spots. But you don't have to do it manually. You can write a program that says, go through this data set of millions of entries and delete every row with an empty in it. And it'll take you like an hour or so for all of that to go through, but when you come back, the data set will be cleaner. And then you say, okay, what's the next error I need to fix? So, yes?
In my company, we pull a lot of data from PubChem or Chemical or chemical molecular structure versus an activity, and we build artificial neural networks to predict this. But what we found is that Bob's age of 132 would stand out after you've trained most of the other data as a big outlier. You go back and study the background information, and maybe it's 13.2 instead of 132. But you can learn. The machine learning will show you where the bad stuff that in your data set is lying.
Yeah, that's a very good point. In statistics, there's this thing called outliers. And it's where if you say like most of your data set is right in here in this area, in this range, and then you've got one that's way over here, then this one's probably wrong, usually. So that's a very good point, Mike. All right. And if you have even one that's way over here and you still put it into the machine learning thing, it might destroy the whole model. It might be bad enough to ruin everything. Okay. So what you do is with categorical variables, the sad thing is the computer cannot understand words. It can only understand numbers. So what you do is you turn these words into numbers. So this category is gender, right? Male or female, so you can just do 0 and 1. Yes. So also with the diet, we've got 3 categories here. So it can be 0, 1, and 2, right? Easy. You just take your categories and you just turn them from words into numbers. So just like that. 0, 1, 0, 1, 2, right? And this is something that the computer can digest instead of the words that we had before. All right, so interesting thing. So we're going back to the example of that really smart kid. You handed him this book so he could train himself, but you took out some of the pages because you wanted to test him, right? You wanted to test him on the chapters that he's learned. So you don't take only the test from the end. You take the tests at the end of every chapter. Because if you only take, the test from the back, then it's only going to test them on the hardest stuff, right? And it's not going to test them on each individual chapter, right? So this is your training data. This is the problems in the book that the child learned on, right? And then you need to make sure that he actually did learn his stuff, so you give him a test, right? You save, okay, I'm not sure if I'm explaining this well enough. Let's say you're trying to teach this kid, you're tutoring this kid for a big exam coming up at the end of the week, right? You have 100 questions that will prepare him for that exam. So you want to train him using those math questions, right? But instead of giving him all 100 questions, you only give him 90 questions because you want him to learn from those questions, and then you want to test him at the end of the week to make sure that he understands it, right? So that is why you have a training and a test set. The training set is how you teach the child, and the test set is how you make sure that the child learned, right? And so your accuracy for the data set comes from running it on your test set. It's trained on this, and then the test set goes through. You already know the answers to the test set. And so if the artificial intelligence gets it correct, then you know that the artificial intelligence is good, right? Okay. You also have to, we don't have to talk about this too much, but big numbers kind of skew things up a little bit. Like we see 100 down here, 150. And if you have big numbers, it kind of messes up everything. So what you want to do is you want to scale it. So everything is around like, -1 to 1. I'm not going to talk too much about that because it's complicated, but this is really important and you always have to do that. And it's as easy as just entering a command. You just say, like numpy.scale or whatever, and it scales your numbers. All right. So, okay, so we were talking about, feature selection. We were talking about how we want to guess a person's weight. That's the label.
Did you say you have to scale all the data to within a certain range?
Yes.
Okay, what range is that?
-1 to 1.
Okay, but what's going on with the weight in the weight column? Why are they higher than 1?
It looks like you can scale the test data, but sometimes what you can do is you scale the training and then you convert it back into the answers back into here. But I mean, I think you normally would scale the test data, so that was my mistake. So good question. You do normally scale the test data as well.
I think he was asking why is 1.35 greater than 1?
Oh, shoot. I don't know. I'm
just for this example, we'll assume that those are all in the range of what you need.
they're closer together than than they would be normally. Like this is how they were, 200. They're pretty big and really far apart. But if you scale them, then they will be, you know, closer together. So, all right. And so as we said, this is our weight. That's what we want our model to guess, which is called the label. All this data right here is fed into the machine so that you can guess this right here. So like how we were talking about how you input images of a cat, right? You input those numbers, and then the label is cat, right? So you're just matching that label to the input. And that's what machine learning does.
So what you're doing here is you're testing your program that you've written, this analyzing all this data.
Absolutely, yes. Yes, and all of this data goes into the program, and then out comes the label. That's the result that we're going for. All right. Okay, so we can delete the pets column because it probably doesn't help us predict weight. All right, so congrats, your data is sparkling clean. I don't know if you guys remember this commercial. It's not fully clean till it's fully clean. It was like back in the 90s. But yeah, so the reason why we deleted the pets column is because you want to delete everything that's not really relevant, because it doesn't really help you, and it kind of dilutes things. You know, it doesn't really matter if the pets are in there, so it can only throw your model off. All right, so data is now sparkling clean. Okay, so now that you've got a clean data set, applying all the techniques that we saw. By the way, I'm filming this, so if I'm going too fast, you guys can like look at it online, or if I'm going too fast, totally tell me to slow down or ask questions. Okay, so let's say you have a data set, right? We cleaned it up. We deleted all the empty rows. We fixed all the errors. We deleted any columns that you don't need, right? So now we get down to training the model, the artificial intelligence, using that data set. So more like model taming. So model taming is an iterative process, which means you do it once and it's terrible. So you go back and you change some things and you do it again and it gets a little bit better. You go back and you do it again and it gets a little bit better. So here is our model from before. Remember, we made this line, which is our prediction or our model, and Mo, we guessed, weighs 250 pounds, right? It turns out I asked Mo, or I overheard somebody talking about him, and he actually weighs 230 pounds. So we were off by how many pounds? 20 pounds, very good. We were off by 20 pounds. 20 pounds is the error, right? The model guessed 250, and Mo's actual weight is 230. So the error is the model's guess minus the actual weight. All right, so okay. So what we're trying to do here is we are trying to move this line around to minimize that error, right? So let's say we had, you know, Jack up here, Mindy down there, Bob over there. We would try to turn this line and move it up and down so that the error is minimized, so that this one line is closest to all four. Does that make sense? That's what regression is. You put in data, right? And then you try to fit a line. You try to make a line that is close to all the points, right? Okay, so this is one way of calculating the error. Instead of just doing like we did 250 minus 230 is 20. Instead of just doing that, you take 20 and you square it, right? You take the error and you square it and divide by all the numbers. This one isn't super important. Just know what it is. It's one of the most popular ways of analyzing whether a model is good or not. So when you see RMSE or root mean squared error, you know it's just making sure that the model is fitting the points. Okay. All right. Okay, so.
Can I ask you one question about that last slide?
Yeah.
So why would you go through the trouble of doing all that when you could just add them all up and get that number, all the errors?
Well, that's a good question. Some of the errors are positive and some of them are negative. Like if we, yeah. As for why we square it, I have no idea. It's really weird. It's like a number convention. We could just use absolute values, but people want you to square it. It's root mean squared error. I have no idea why they do that.
So then this formula is something that was derived from reality, from when they were trying to figure out how to do this in the first place, they found out that that worked better than other methods of dealing with the error?
You know, I think it comes from statistics, actually. Yes?
Okay.
If one of those weights was below and the error was negative, and you square it, it comes out positive.
Yes. Mm-hmm.
And so if it was positive and you square it, it comes out positive.
Mm-hmm.
If you add them up and take the square root, you get a measure of the overall error that you're trying to minimize. Whereas if you had not squared it, they would have been some up, some down. You wouldn't have had a real estimate of the total error. That's what the root mean square error does.
But what about using absolute value instead of square?
Well, that's, absolute value would be appropriate.
Okay.
I can't tell you exactly why absolute is not generally used for
It'd
that.
probably be easier to just square everything than it would to go through it and parse for negatives and positives.
Could be. I'm not positive.
Yeah, it could be.
So this is likely a formula that came from statistics, not something that they cooked up just when they started doing machine learning data set stuff.
Yeah. There's actually. Oh,
They
go ahead.
use this a lot in AC voltage.
Really?
For the same reason, because it's positive and negative over. And
Really? They use root mean squared error in AC voltage.
I don't know about the error part. They use root mean squared.
Okay.
When you're looking at a AC voltage reading, you're looking at root mean squared.
That is really interesting to me. Apparently it's useful in a lot of places. There's a joke online about the relationship between statistics and machine learning. There's like a crack on the wall, and underneath it says statistics. And then a guy takes an empty picture frame and he puts it over the crack, and then it says machine learning, and there's this big crowd around it taking a photo, as if it's art. So, all right. So AUC and confusion matrices. So we were talking about how to score a regression model. Remember, so far we've talked about two different types of machine learning. There's categorizing pictures of cats, and then there's regression, figuring out how much your friend weighs, right? So we just talked about a way to tell if your model for how much your friend weighs is awesome, if it's good. And now we're going to talk about how to tell if your classifier for cat images is good. Okay, so we use area under the curve, which I'll explain in a minute, and confusion matrices. So what's wrong with this? What's wrong with these labels?
The cat is not. The cat is a cat.
Well,
Yep, good.
yeah,
Where's another error?
the dog.
The dog.
Yep, the dog is labeled as cat, right? So the problem here is some of these are mislabeled, and there's specific names for the type of mislabeling. You know what, there's a really funny meme about this, and I wish I'd brought it. It's about like this doctor telling a guy that he's pregnant. But, so this one right here is a false positive, meaning it says this is a cat, but it isn't, right? So it's a positive, it's saying, I am positive that this is true, but it's false, right? This one is a true positive. He's saying, it's true that this is a cat, positive, and it's actually true, right? I'm positive about this being a cat, and it's true. This one is a true negative because the machine is saying it's negative, and that assertion, oh, do you have to leave? Okay. All right. Thank you for stopping by. Make sure to grab some water.
I have some.
Okay.
And I have coronavirus.
All right. I hope you feel better. Okay. All right. I'll wait for the gentleman to get back. Actually, you didn't hear this, I don't think. Okay, so first one with the dog. It is a false positive because the machine is positive that this is a dog, but that's false, right? Or I'm sorry, it's positive that this is a cat, but that's false. This one is a true positive. The machine is positive that this is a cat, right? And it's true. It happens to be true. This one is a true negative. The machine is negative that this is a cat. The machine says no, that this isn't a cat, and that happens to be true. It happens to be accurate, right? And for the last one, can anybody guess what this one is called?
False negative?
Yes, very good. You got true negatives, false negatives, true positives, false positives. Very good, Jonathan. Okay, false negative. Perfect. Okay, so this is a confusion matrix. Actually, I'll wait for the other gentleman to get back. But going back to this slide, we have one false positive, one true positive, one true negative, and one false negative, right? So if we go to this slide, all we do is we just make a little chart. We say we've got one true positive, one true negative, one false positive, and one negative. And that's what a confusion matrix is. Now, normally, under regular circumstances, you wouldn't just have 4 images. You would have, maybe a couple hundred, so you get a better statistic. And hopefully, you don't have very many false negatives. And hopefully, you don't have many false positives either. A false positive is if the doctor says, you've got cancer, when you don't actually have it, right? So that's a false positive. A false negative is when the doctor says, you don't have cancer, you're in the clear, but you actually do have cancer, right? So you want true positives and true negatives. A true positive is the doctor says, you've got cancer, and you actually have it. True negative is the best one. The doctor says, you don't have cancer, and it's true that you actually don't have cancer, right? So this all happens after your model was trained. After your model was trained, what was your name again, sir?
Will.
Will. Okay, so we're just talking about confusion matrices. You've got false positive, true negative, false negative, right?
Okay.
Then you just make a chart. True positive, you got one. True negative, false negatives, right?
Yep.
Okay. So let's say we're doing disease testing. So can somebody explain this graph to me?
So there were 3,000 cases that were confirmed.
Perfect.
Five that were proven or that were wrong. No, 5 that were confirmed not to have it.
Perfect. Very good. Yes. Okay. Can somebody explain to me what happened in this column?
There were four that were falsely claimed to be positive. We said it was a dog. And
Perfect. Perfect.
And one that said this is definitely not a dog, and it was.
Perfect. Yes. Very good. Perfect. You guys are on top of this. It took me forever to learn this. You guys got it in like 10 minutes. This is awesome. Okay. So we have a lot of true positives here. It's like 99.999%. So this test for diseases is very, very accurate. So, but we also have some false positives, which is pretty bad. Okay, so the area under the curve is the false positive rate versus the true positive rate. Like if you, okay, so let's say you make your model really, really lenient, as in you make it so that your model classifies everything as a cat. You will get a true positive rate that's huge because every single image that goes into it of a cat gets classified as a cat. So your true positive rate is amazing. However, your false positive rate would be really, really bad because every image that you feed in it of a dog also gets classified as a cat, right? So this is a trade-off between the true positive rate and the false positive rate. You have a little threshold in here, like let's say this one's really good. This one's like, I don't know, 10%, right? This is really good because you were classifying 90% of the cat photos correctly and you only get a false positive rate of 10%. This would be a really good model right there. But if you go further, if you say, I want more accuracy, I want more cat photos to be classified correctly, then you have a trade-off because your false positive rate increases, right? So that's what this graph is. It's the area under the curve. So the farther up and to the left this is, the better. right? This one is not so good because it's not as close. Like if you want to maximize if you want to get up to 80% true positive rate, you're going to have to accept around a 40% false positive rate. As in, you know, if you want to catch 80% of the diseases, you're going to have to suffer through 40% of the people taking the test being incorrectly classified as having the disease. So this one isn't very good, and this one is worthless. That line right there, that's nothing. So if your model the farther your model bends out from this, the better. If it's all the way up in the corner, it's amazing. Okay, overfitting versus underfitting. In machine learning, you will hear the term overfitting a lot. And I was very confused about this term because I thought, don't you want the model to fit? How can a model possibly be too good? Well, the fact is, if a model is too good on your data set, then the model will not generalize. Like, let's say you practice one skateboarding trick for years. It is just one skateboarding trick. You become amazing at that skateboarding trick. But if somebody else says, hey, you want to be in a skateboarding competition, when you're skateboarding, you're going to have to do other tricks. You're not going to be able to do those other tricks because you didn't learn them. You're only going to be able to do that one trick. And even if you try to do other tricks, you might return to muscle memory and you might just do that same trick again. So the thing that you learned does not generalize well. That's overfitting. You train too much on one thing, so your model becomes too specific and it doesn't work on other things. Like, here's an image that I like to use. Here's a model and she fits her chair. So the model fits the data, right? This is the model that is underfit. She does not fit her chair. You'll see her planking on it right there. She does not fit at all, and this is a result of not training very much. And this is a model overfitting. She fits the couch too well. And if you froze her and you moved her to another chair, she would not fit in that chair because she is too accustomed to this couch. Okay, here's an actual example of what it'll look like. So we can clearly see a pattern. It's like a little swoopy, little Nike swoosh right here in the data, right? And right across here we have our model. Remember our regression line that we had, and it doesn't really fit the data very well, right? It's just going about its business. It doesn't really know what it's doing. So this one is a good fit, right? Because it kind of reduces the error and it approximates that line, right? It's like close enough to be good for predicting things. Like if we predict something along this line, it's probably going to be pretty accurate. I mean, there are some that are off, but it's going to be pretty close. This is overfitted because the line is drawn to minimize error for each and every point, right? And so if you try to predict what happens at this point right here, it's going to be either way up here or way down there. It's not going to be useful for anything except for just this data set. And that's not what you want. Like we talked about having 50,000 images of cats and training a computer to recognize cats from that image data set. Do you want this machine learning model to only recognize cats that were part of that data set, or do you want it to recognize all cats? If you do this, it will recognize all cats, no matter what new cats it sees. If you do this, overfitting, it will only recognize the cats that were in that specific data set. It will not generalize to new data.
I was at a conference and Russ Altman from Stanford was talking about his students building a net that would take a look at 10,000 images of faces and pick out all the previous presidents.
Oh!
When he was finished, I said, well, do you think your net would be able to pick out the next president from the group of Democratic candidates who are available? And people kind of snickered and laughed a little bit. But he said, yes, I understand completely. This is one of the biggest problems I have with my students in overtraining.
Yeah. Okay. Well, first of all, that's a really good idea because I've seen, I saw a show where people were able to look at photos of two people who were in a political race with each other. And they were able to pick out the winner just from the photo like 70% of the time. So what you're talking about with that machine, it might be possible. You might be able to put, you know, all the faces in it and see who is going to be the next president.
There would be something general on it. That's good.
Yeah. All right. So we talked about overfitting. It's really bad. How to do it. Here's how to do it so you can avoid it. If you have too many features, like remember we were talking about when we were trying to predict somebody's weight and we had their address in there and their number of pets. Those don't matter. And if you have too many columns, then you're going to end up with something looking like this. It's not very good. So you want to delete columns that don't matter or that matter very little. You want to focus on the features that are important. Okay. Also, the coefficients of the variables are too large. So this is an equation, right? Like this is y equals mx plus b. You know, just it's an equation for a line. This is a different equation. This is a crazy equation. This one only has one coefficient. I mean, we're talking about algebra here, but that's the slope. This one has a couple coefficients, maybe an x squared in it or something like that. This one has a ton of little coefficients because it's like a much more complicated equation. Like, this is not a complicated equation. You can just look at it. This is a little bit more complicated. This is tremendously complicated. I don't even know what this is. It's got so many parameters, we don't know what to do with it. So if you want to have a good fit, make sure that the equation that you come up with for the line is fairly simple. You know, don't have tons and tons of terms on it. You want to limit the complexity of that equation. Okay.
Those graphs remind me of in CAD drafting, B-splines and Bezier splines and how they follow every little dot or to generalize.
Yeah, I took a class on CAD drafting. It's actually really fun. I really enjoyed that. Okay.
I gotta go.
Oh, see you later.
Yeah.
Later, Jonathan.
Thanks.
Okay. We're actually going to take a break in a couple minutes, but okay.
Oh, I'll just stick around.
Oh, well, okay. So this is what I talked about right here. This is algebra. You've got y equals mx plus b. M is the slope, right? It's not very complicated. It's just one coefficient of a variable. And also, if your coefficients are too large, that's probably overfitting. Like, look at this. 538 times x plus 34 times x2 plus 0.003 times x. If you have a really, really big number like that, your coefficients are probably too large, especially if you've scaled all of your factors already. Okay, one more thing before we take a break, cross-validation. It's very interesting, and there are lots of different types of machine learning models. You have a data set, you choose how you want to predict on it. You could draw a line, you could draw a swoopy line, you could use decision trees, you could do all of this different stuff. There are many, many different types of models. How do you know which one is the best? So you do this thing called cross-validation. You have your data right here, right? And you divide it into 5 different, well, you can divide it into however many buckets you want. But for this example, we're going to use 5. So you say the first bucket is training data, second bucket is training data, all the way over to here, your test data. So what you do is you pick a model, like let's say the line. We pick that model. And so we train that model on these guys and we just test it on that one. Then we see how well it does. Is it a good model or not? We do that with the root mean squared error. Remember, we try to minimize the root mean squared error. If that's really small, then we're like, okay, this is great. But we're not done there. We go back and we use the exact same data, right? Except the first bucket is the test set now, right? So then we do it all the way through until we've got all of them switching off between the training part of the data and the test part of the data. This is all the same data, right? We just divided it into 5 buckets, and test, whichever one we use to test it gets switched around. So this is a way of testing that model 5 different ways on the same amount of data. And so then we get 5 different answers for its accuracy, and then we average those together, and if it's really good, then we say, okay, that's a good model. Then we try a different model. We do the same thing. This is called cross-validation. And then we go through another 5 times, we average it, and then we say, okay, this model had a root mean squared error of like 0.5. This model had a root mean squared error of 0.2. So this one is better. We're going to use this one, the one that had the lower root mean squared error. If you only do it once, if you only do just training and test once, you probably won't get the best and most accurate answer for your question, because sometimes models are good and bad depending on the data you put into them. Okay, take the average. This doesn't work just for choosing models. It also works for tuning models. As in, you've got a model and you've got all this other stuff about it that you need to specify. Like you need to specify how many extra variables you want in it, how big you want the coefficients to be, like we talked about earlier. A lot of that is preventing overfitting. So you choose algorithms, choosing features, etc. So anything that you want to change about your model, your machine learning algorithm, which is a program for processing data, that's what an algorithm is. Anything that you want to change about it, you can do trial and error through cross-validation to figure out which tweaks are the best, which tweaks make your model the most accurate. Okay, all right, so let's take a 5-minute break and then we'll come back.